Welcome everyone to lecture number 44, chemistry, okay, part 2. We're going to talk about electron configuration, and what I'm going to do is I'm going to build on the silly stuff I said in the last lecture about a hospital. If you'll recall, I said I was building a hospital on the first floor. There were 2 surgery rooms, 2 S rooms, and then as I became, you know, better known as a surgeon, I was able to build a second floor, so I put 2 surgery rooms there. But my rule was I couldn't put anyone on the second floor until my first floor was finished. And then I also on the second floor, I put 6 proctology rooms, once again holding to my rule that I cannot put anybody in a higher room until I fill up the first floor, the first 2 surgeries, the second 2 surgeries, second floor 2 surgeries. Then I can start filling those 6 proctologies rooms, the P rooms on the second floor. Once those are filled, so I have 2 on the first, 2, and then 6 is 8 on the second. Once those are all filled, I build a third floor, once again, 2 surgery rooms, 6 proctology, etc. Why am I calling them S and P? Well, for my hospital, surgery, proctology. In chemistry, S and P come from long German words because German spectroscopists named these. So the words are in German over 150 years ago from laboratories such as Bayer, as in Bayer aspirin, and so forth. So they were early scientists working on the spectroscopy or colors of atoms as the electrons, remember, go to different energy levels. All right, so that's where the sp, then d, and f, and all the higher orbitals are named. All right, so I want to go back and look at our periodic table. Okay, so hopefully you have a copy of a periodic table. It's very important for the third exam and the material we'll be doing. My estimation is about 80% of the third exam, the last exam, will be getting information from the periodic table, how to read the periodic table, how to interpret, and so forth. Once again, for this class, this level, we're not going into crazy detail as one would in a real rigorous chemistry class. Those of you who want to become nurses will eventually have to take a serious chemistry class. Okay. All right. Let's look. First thing we're going to look. We're going to look at hydrogen. Hydrogen has 1 electron. So I'm going to say in the language of the last lecture, on the first floor, I have 1 surgery. Okay, that's silly, really not that. Okay, the next one is helium with 2 protons, so there are 2 electrons. Once again, on the first floor, I have 2 in the surgery room. So that's first floor, 2 in surgery. Now, after helium, lithium has 3 protons, so lithium atom has 3 electrons. So the first 2 electrons fill up the first floor, 2 electrons or 2 patients on the first floor. Now I go to the second floor surgery. Beryllium, fill up the first floor surgery, fill up the second floor surgery. Okay, S. Now, when we get to boron, we fill up the 2 S's, the 2 surgeries. Now we start with the proctology. Okay, so on the second floor, we have P. Then we go to carbon, 1 more electron, we have 2 in the P. Nitrogen, 3 in the P, proctology. Oxygen, 4 in the P. Fluorine, 5 in the P. Neon, 6. Okay, I'm going to write this as neon. So this configuration is going to represent neon. Okay, you'll see why I'm going to do that. And this is a typical chemist notation. Okay, this way I don't have to keep rewriting everything over and over again. Okay, so 1s2, 2s2, 2p6 has a total of 2. 2 is 4, 10 electrons. So the first levels, the first S floor is filled, the second S floor is filled, and the second proctology is filled. So the first 2 levels completely filled. Now we're going to go, obviously, to the third floor surgery. Okay? So the next element in the periodic table is sodium. So we have the neon configuration, and then we go to the third floor surgery, 1 electron or 1 patient in third floor surgery. Magnesium, third floor, 2 in the surgery. We move to aluminum. Okay, we have the neon configuration. The surgery on the third floor is filled. Now we start filling the third floor proctology. So aluminum has 1 electron, silicon has 2 electrons, phosphorus has 3 electrons in the third floor proctology or P shell. Sulfur has 4 electrons, chlorine has 5, argon has 6. So again, so that's it for third floor. We filled it. So I'm going to call this AR. Okay, and then we just one or two more, right? Potassium has the argon configuration, and then we move to the fourth floor, 4s1, calcium 4s2, and we'll stop there. We're not going to go, as I said, into crazy detail. All right. What we're doing today is we're only looking, if you have a periodic table, on the top, the group numbers or in the columns, hopefully it has some A groups and B groups. We're only looking at the A groups. The A groups are on the left, the first two columns, and the last 4 or 5 columns on the right. Okay? In the middle are B groups. We're not doing B groups. We'll do those another lecture. We're just doing A, okay? Just doing A. All right? So look only at A groups, the columns 1A, 2A, 3A, 4A, 5A, 6A, 7A, 8A. Okay? So let's look at 1A. If you look at 1A, what's in 1A? Well, you see hydrogen has 1s1. Lithium has 1s2, 2s1. Sodium has 3s1. Potassium has 4s1. Okay, so I'm going to circle this. 1s1, 2s1, 3s1, 4s1. You get the idea? Okay. Uh, so anything in group 1A has a 1s. Okay. Group 2A, let's look. Helium, we won't worry about. It's kind of crazy. Helium's a little special, but it has a 1s2. Beryllium has 1s2, 2s2. Magnesium has a 3s2. Calcium has 4s2. 1s2, 2s2, 3s2, 4s2. Group 2A. 1s1, 2s1, 3s1, 4s1, 1A. We're trying to look for patterns, okay? Right? We all know that this is all due to Mendeleev, right? Mendeleev. Sorry. Okay, Mendeleev. This was his chart. All right, the periodic table. All right, 3A, you're getting the idea, right? What does 3A have? Well, 3A, we fill up the S, and now we have 1 in P, right? 2P1. Aluminum, 3P1, and so forth. Germanium, etc. Now, why is it group 3A? See, here I see a 2. Here I see a 2. I see a 2. Here I see a 1, a 1, a 1, a 1. I see a 1. Now I see a 3, but I see a 1. But let's think about what's on the top floor. On the third floor, we have 2 surgeries, 1 proctology. So the total number of electrons or particles or patients on the third floor is 3. 2, 1, 3. Okay? So this number before the A, the Roman numeral 3, means there's 3 electrons on the top floor. Later we'll call this the valence shell, the top shell. 2 electrons on the top shell. 1 electron on the top shell. Well, you can guess now. Let's just jump to 6A, okay? Let's do 6A. So oxygen has how many? Well, there's a 6, right? So on the second floor, there's 2 plus 4 is 6 electrons, 6 patients. Go to sulfur below oxygen. What do we have? We have the neon configuration filled up. On the third floor, the top floor is third floor, 2 plus 4, 6. Okay, so we're trying to find the pattern. We see the pattern, and then we'll see how this affects the chemistry of what's going on. All right, let's jump to 7A. We have fluorine. All right, you can guess there's a 7 there. So how many electrons or how many patients are going to be on the top floor? 7. So what do we have? On the second floor, we have 2 plus 5 on the second floor is 7. Chlorine has the neon configuration. Third floor is the top floor. How many electrons? How many patients? 2 plus 5, 7. Okay, and then finally group 8A, the noble gases, the inert gases. So we have neon, which has how many electrons on the top floor? It has 2 plus 6. Top floor is second floor. So there's the 8. Right? Argon has the third floor. 2 plus 6 is 8. Okay, so the Roman numerals for the A groups are really telling you how many electrons or how many particles are on the top floor. All right, we're going to call those the valence. So we're going to deal with the A groups right now. Okay, all right. let's talk. Let's talk about lowest energy state, okay? An octet rule. I'm just going to erase some things here. Okay. Lowest energy state. Lowest energy state. What is the lowest energy state for an atom? Okay, I'm gonna give you two little rules, very simple. Okay, one is going to be called the octet rule. What does octet mean? Octet means 8. It means it wants the top level to have 8 electrons. That's a lower energy state. It's the lowest energy state. Okay, 8 electrons. Okay, and I'll show you that in a second. Okay, the second thing we're going to say is the top. I'll write the word valence here. Level is full. Okay? It's full. You can't fit anymore. So the lowest energy state for an atom is where the top valence level is full. So that's what an electron wants. That's what the atom wants to do. All right, so we're going to talk briefly and then get into this in more detail in the next lecture. So let's look at 1s. Let's look at the 1a, okay? Let's skip hydrogen for a second. Let's look at lithium, sodium, and potassium, okay? Let's look. For lithium, lithium has one electron on the second floor. Remember, the second floor has 2 s's and 6 p's. So the second floor can hold 8 electrons. So if I want to follow the rule, an octet rule, then what would happen is lithium would need 7 more electrons to make 8 electrons in the top level. So again, the second level can have 8 electrons, but there's only 1 electron there. So the lowest energy state would be to have 8 electrons. So lithium could add 7 more electrons. But this rule, top valence level is full. How could that be? Well, again, that would give you an octet rule. If you add 7, the second level would be full, and you would have a full level, and you'd obey the octet rule. However, if we look at this for a second, if this lithium got rid of, I'm going to cross this out, got rid of 1 electron, then it would just have a 1s2. That means the top level, the first floor would be full. That would give us the second rule, right? The top valence level is full. So what would you think is easier in terms of energy? To gain 7 electrons or to lose 1 electron? Okay, so obviously lithium wants to lose 1 electron. If you lose 1 electron, then you have 1 more proton and electron, so you have a +1 charge. So this wants to be an Li +1 ion, right? Because it's going to lose an electron. And the same is true for sodium. It could gain 7 electrons to fill up the third floor or lose 1 electron. So it loses 1 electron, becomes sodium +1. Potassium, same thing. Add 7 electrons to the fourth level or lose 1 electron to make the third level full. So it loses that and it wants to be K +1. So every element in group 1A wants to be in its lowest energy state, so it wants to give away an electron, okay? Give away an electron. You can guess what's going to happen in 2A. 2A, same argument. There's 2 electrons on the second floor. It could either add 6 to make the octet and complete the top floor, or it could lose 2. Which is easy to do? Add 6, lose 2. So group 2A wants to lose 2 electrons. Lose 2 electrons, 2 electrons. So everything in 2A wants to be, I'll call it X +2. wants to be a +2 positive ion, wants to give 2 electrons. If you're in group 2A, you want to give away 2 electrons. Same thing, group 3A. How many electrons there? Well, it's got 3 in the top floor. It could add 5 or lose 3. Add 5 or lose 3. So it's easier to lose 3. If you lose 3 electrons, these things want to be a +3 ion because they want to lose 3 electrons. Lose or give away. Things that want to give away electrons, group 1A, 2A, 3A, are called metals. So I'm going to write this here. So metals give electrons. All right? And so they want to be positive ions. So they want to be cation ions. So group 1, 2, 3 want to give away electrons. Those are called metals. Metals are like women. They're the givers, okay? You can guess what a nonmetal is. All right, let's jump to group 6A. Something like oxygen. Well, oxygen has what? Has 2 plus 4, has 6 electrons. So oxygen could either lose 6 or just gain 2 electrons to make the octet and to complete the top floor. So what would you think oxygen want to do? Lose 6 electrons, gain 2. Well, if it gains 2 electrons, it has 2 more electrons than protons. Oxygen wants to be a -2 anion, right? Wants to be a -2 ion. Same with sulfur. Third floor. It could lose 6 electrons or gain 2 electrons. Sulfur wants to be -2. So everything in group 6 wants to be a -2 ion. In other words, what it wants is you want to add electrons. Add electrons. Or take electrons if you want. Okay? So metals give electrons. Things that take electrons, you guessed it, called nonmetals. Nonmetals. And then we can finish with group 7A, right? 7, you can lose 7 electrons, gain 1 electron, and you become -1 ion. So fluorine wants to be a -1 ion. Chlorine wants to be a -1 ion. So everything here wants to be -1, wants to gain 1 electron. If you're in group 5A, remember 5A, you can lose 5 electrons or gain 3 electrons. Everything in group 5A wants to gain 3 electrons. Group 4 will have something to say later, whether they gain or lose. For example, carbon has 4 electrons, right? Carbon can either lose 4, give away 4, or take 4. If it loses 4, we would consider it a metal. If it gains 4, we would consider it a nonmetal. Clearly, carbon behaves more like a nonmetal, so carbon's preference is to gain 4 electrons, okay, to become -4 as a charge. All right. Finally, group 8A, look, there's 8 electrons there, neon. There's 8 electrons for argon. Everything in group 8A already has 8 electrons. The top level's already full. The top level, the electron configuration already is in its lowest energy state. So everything in group 8A will not interact. Okay, they're already happy. They're already in their lowest energy. These are the inert gases, noble gases, ideal gas. They're perfect. They don't interact. They don't care about anybody because their top level is complete. Okay, and so they will not combine. So you won't get argon mixing with something else because they're already happy. Now, if we just look very quickly, we said that everything in group 1A wants to give away an electron. Okay, so I'm going to pick sodium just for now. Let's pick sodium. Na wants to give away an electron and become +1. Okay, that's 1A. Okay, let's look at group 7A. Right? What does 7A want to do? Like chlorine, they want to become a -1 ion. They want to add an electron. Sodium gives 1 electron. Chlorine needs 1 electron. Give, take. Give, take. You have a plus ion. You have a minus ion. Okay? So this gives one electron, this takes one electron. So we have our famous table salt. We'll name it in a bit, sodium chloride. Okay, because you have a plus ion with a minus ion, this is called an ionic bond. Okay, so ionic bonds are going to be between metals and nonmetals. Okay, give one electron, take two electrons. Take one electron. Okay, suppose, let's do simple and then we'll end here and then we'll pick this up in the next lecture. Suppose I want, let's take sodium again. Let's take potassium. Potassium again wants to give one electron, wants to give one, like it's in group 1A. Let's look at sulfur. Sulfur needs two electrons. But potassium only can give one electron. So sulfur needs two electrons. How could potassium mix with sulfur and make it happy? Well, one potassium cannot. But if we take two potassiums, gives an electron, needs two electrons. So our formula then would be this. Two K's we'd write as K2S. Okay? And we'll name this in a bit. Okay? Potassium sulfide. All right? Give two. Each one gives one electron. This needs two, so it takes two of them. Suppose I wanted potassium, right, which wants to be plus one, wants to give away one electron. Suppose we want to mix it with nitrogen. Nitrogen needs three electrons. Remember, nitrogen is in group 5A. So nitrogen has five electrons. It can lose five or gain three. If it gains three, it has a charge of -3. So nitrogen needs three electrons. Potassium gives one electron. So you need another potassium to give an electron, and you need another potassium to give an electron. So since nitrogen needs three electrons and each potassium gives one electron, you have 1, 2, 3 potassiums with one nitrogen. We would write this formula as K3N. Okay, once again, we'll be naming this in a bit. Potassium nitride. Okay, 3 potassiums, 1 nitrogen. All right, let's start. Let's do the naming. Since you know sodium chloride, and I've been saying these names. Let's look. So naming ionic compounds. Okay, what we do is we take the name of the cation, add it to the root of the anion, the negative ion, and add the ending IDE. Okay, so we know NaCl. Sodium is the name of the cation. Chloride. Ks. Oh, what do we have? K2S. Potassium is the name. Sulfide. Okay. Let's see if we can mix. Let's see if you can do this one. Suppose I wanted M, G, and O. We'll give you an easy one, okay? Well, what's the name of this, first of all? Okay. First of all, it's magnesium oxide, ionic bond. If you'll recall, magnesium's in group 2A. Magnesium wants to be +2, wants to give 2 electrons, but oxygen wants to be -2, needs 2 electrons. So the formula for magnesium oxide is simply MgO. Suppose I wanted magnesium chloride. Well, Mg, right? It's giving 2 electrons. Chlorine only needs 1 electron. So how could magnesium mix with chlorine? The answer is these 2 electrons have to go somewhere. But so 1 electron goes to the chlorine because it only needs 1. So you get another chlorine, right? They each need an electron. So what's the formula? Magnesium chloride, MgCl2. You need 2 chlorines. All right. Suppose, and then we'll end in a second. These are all ionic bonds. Why? Because they're between positive ions and negative ions. They're between metals and nonmetals. Okay. How about you try aluminum oxide? Okay. Or calcium nitride. Okay. So try these and I'll do them for you. And hopefully I'll get them right and you'll get them right. Better that you get them right than I get them right. So aluminum, remember aluminum's group 3A. So aluminum wants to be plus 3, right? It's giving 3 electrons. Okay. Oxygen needs 2 electrons. How in the world can we make this go with this? This gives 3, that needs 2. Well, it's like finding the common denominator, 3 and 2. So watch what I'm going to do. Al wants to be plus 3. Oxygen wants to be minus 2. So just watch for a second, see if you understand, okay? If I take 2 aluminums, 2 aluminums gives 6 electrons, doesn't it? 2 times 3. Well, that's 6. So that's giving 6 electrons. How can oxygen take 6 electrons? Well, each oxygen needs 2 electrons. So if I take 3 of those, 3 times 2 is minus 6. 6 minus 6, 0. So it gives 6, takes 6. 2 of these giving 3, 3 of these taking 2. So the formula for aluminum oxide would be Al2O3. So a test question. What's the formula for aluminum oxide? Al2O3, Al3O2, AlO3, etc. I would have these multiple choice questions. How do you know what to do? You simply go to the periodic table. Good? Let's look at calcium nitride. Okay? So I'm going to do this one a little quicker. All right, so calcium is in group 2A, wants to give 2 electrons. Nitrogen is in group 3A, needs 3. So it looks very much like this one, but they're reversed. So calcium's giving 2 electrons, but nitrogen needs 3 electrons, right? It's 5 electrons, so it needs 3 to become an octet or to fill the top level. So if I take 3 calciums, again, that's giving 6 electrons. So this takes 3. If I take 2 nitrogens, that takes 6. Right? 3 times 2, same as 2 times 3. So the formula for calcium nitride, Ca3N2. And these are examples of ionic bonds. Ionic bonds. Ionic bonds. And ionic bonds, remember, are between metals and nonmetals. Once again, we're only looking at the A groups. All right? How about strontium iodide. Hmm. How about aluminum phosphide? All right, let's do these quick, and we'll call it a day. Strontium is in group +2, group 2A. Iodide is in group 7. So strontium wants to give 2 electrons. This needs 1 electron. This is giving 2. There's only 1. So we put a 1, 2. So the formula would be Si2. Strontium, SR. Sorry, I put sulfur. Strontium iodide. Okay, give gives 2 electrons, needs 1 electron, so we need 2 of those. So strontium iodide, Sr. Okay, and then finally aluminum phosphide, phosphorus, P is in group 5A. So phosphorus wants to be -3. Why -3? Because it's in group 5. It needs 3 electrons. Remember, it's a nonmetal, and it wants to take electrons. So aluminum +3, phosphorus -3. Gives 3 electrons, takes 3 electrons. So that's the formula, ALP. Aluminum phosphide. Gives 3 electrons, takes 3 electrons.